Welcome to Descriptive Statistics. Today, we are going to explore one of the most important concepts in probability, mathematical expectation. If you have ever wondered how casinos always make money or how insurance companies set their rates, you are about to find out. Let us start by imagining a simple coin toss game. If it lands on heads, you win $2. On tails, you lose $1. If you play just once, the outcome is highly unpredictable. But what if you play 1,000 times? You will start to notice a very predictable pattern in your average winnings per game. This long-run average outcome of a random event is exactly what we call mathematical expectation. Now that we understand the intuition, let us look at the formal definition. Mathematical expectation is the weighted average of all possible values a random variable can take. Instead of just adding up values and dividing by the total count, we multiply each possible value by its probability. This means that highly likely outcomes pull the average strongly toward themselves, acting like a center of gravity for the entire probability distribution. This brings us to the mathematical formula for discrete variables. E of x represents the expected value. To calculate it, we take each specific value, xi, and multiply it by its probability, p of xi. The Greek letter sigma tells us to add all these products together. If a value has a high probability, it contributes a large amount to the sum, pulling the expected value closer to itself. Before we move on, let us see this formula in action with a concrete example. Suppose you roll a standard, fair, six-sided die. What is the mathematical expectation of a single roll? We start with our discrete expectation formula. Since the die has 6 faces, we sum from 1 to 6. We substitute the actual values. Each number from 1 to 6 is multiplied by its probability, which is 1/6. Continuing with our calculation, because the probability is the same for every single outcome, we can factor out the 1/6. This simplifies the math to just adding the numbers 1 through 6 and dividing the total by 6. The final expected value is 3.5. Notice that 3.5 cannot actually appear on a single roll. This perfectly illustrates that the expected value is a long-run average. To truly grasp what this 3.5 means, let us look at this diagram. You are seeing the probability distribution of the die roll. Each blue block represents the 1/6 probability of rolling a 1, 2, 3, 4, 5 or 6. The triangle underneath is the fulcrum or balancing point of these weights. It sits exactly at 3.5. This is why we call the expected value the center of mass of the distribution. Now that we have mastered discrete variables, what happens when our data is continuous? Continuous random variables can take any value within a smooth range, like exact time or exact weight. Because there are infinitely many possible values, we cannot simply add up discrete probabilities anymore. Instead, we have to sum up an infinite number of infinitesimally small slices to find our long-run average. This continuous approach gives us a new formula. Instead of a summation sign, we use the integral symbol to sum across the entire range from -infinity to +infinity. Here, f of x is the probability density function, which tells us how densely the probabilities are packed around a specific value x. The term dx represents a tiny, microscopic width of the value range. Just like before, this calculates the center of mass. This formula we just saw leads us to an important question. Does an expected value always exist? The answer is no. For the expected value to be mathematically valid, the sum or integral must be finite. If the tails of a probability distribution are too heavy, meaning extreme values have unusually high probabilities, the average refuses to settle down to a single number. A famous example is the Cauchy distribution, where extreme values pull the average infinitely in both directions. Moving past those pathological cases, let us look at one of the most powerful and forgiving rules in all of statistics, the linearity of expectation. This rule states that the expected value of a sum of random variables is simply the sum of their individual expected values. The most beautiful part of this property is that it holds absolutely true regardless of whether the variables are independent or heavily dependent on each other. Let us look at the mathematical form of this rule. In this equation, x and y are two different random variables, which could be completely related or completely unrelated. The letters a and b represent constant numbers, like multipliers. The formula proves that you can pull constants out of the expectation bracket and split the addition into two separate expectations. If you double the value of x, its expected value simply doubles. Before we move on, let us see this linearity rule with a concrete example. A business owner runs an ice cream shop and an umbrella stand. The daily profit from the ice cream shop, X, has an expected value of $200. The umbrella stand, Y, has an expected value of $50. These are highly dependent because sunny weather boosts ice cream but ruins umbrella sales. We need to find the expected total daily profit. Continuing with our calculation, even though the profits are heavily dependent on the weather, we can still find the total expected profit easily. We use the linearity of expectation formula, which allows us to break the complex combined profit into two simple separate expected values. We substitute 250 into our equation. The total expected daily profit is $250. The dependence between the weather and the shops does not break this rule. While addition behaves beautifully with expected values, multiplication is a completely different and much stricter story. A critical distinction that trips up many students is assuming that the expected value of a product is always the product of the expected values. This is absolutely not true in general. This equality only holds true under one very specific condition. The two random variables must be completely independent of each other. Here is the formula for the expectation of a product. This specific equation is only valid if and only if the random variables x and y are strictly independent. Independence means that knowing the outcome of x gives you absolutely zero information about the outcome of y, like rolling a die and flipping a coin. If they are dependent, this formula breaks down completely, and you must use their joint probability distribution instead. Now that we understand basic combinations, what if we only have partial information? Sometimes we do not know the overall average of a variable directly, but we do know its average under certain specific conditions. The law of iterated expectations, also known as the Tower rule, provides a brilliant way to find the overall average by averaging the conditional averages. It essentially states that your best guess of your best guess is simply your best guess. Let us look at how this is written mathematically. In this nested formula, the inner term represents the conditional expectation, which is the expected value of x given that a specific value of y has already occurred. Because y is still a random variable, this inner expectation is itself a random variable that changes depending on y. The outer e then takes the average of all those conditional averages, leading you right back to the unconditional expectation of x. We have covered a lot of ground today. To summarize, mathematical expectation is the foundational pillar of probability, acting as the long-run average of any random process. It simplifies complex events into a single number, representing the center of gravity for the data. By mastering properties like linearity and the law of iterated expectations, you can easily break down complicated real-world problems into manageable pieces. You now have the tools to predict what the future holds on average.